Okay, so last day we finished binary heaps, and then we started this more types of augmented tree data structures motivated by different problems. So first problem is multi-increment problem. So here you are given a list of elements, integers, and your operations will be. So you want to design a data structure such that the operations are, you want to increment I to j, xi to xj, all of them by delta. Or you want to report the value of an xi. Okay, and everything should be extremely fast. Preferably constant time. If not constant time, then log n time. Okay, so here we use interval tree. This is a highly specialized augmented tree data structure which arranges the array or the list of n integers in the leaves of a complete binary tree, and above that you have these internal nodes which actually represent intervals. Okay, so the skeletal interval structure is in the first example, and then how you will do multi-increment is in this example, second example. Okay, so 0 to 6 means 4 to 29 values. Okay, so you want to increment them simultaneously by plus 10. So instead of going sequentially, what you will do is you will go above in this interval tree, parents and ancestors, and you will write 10 there. Is this clear? So you will write delta in the correct places. So we have this idea of the steps. So you have to see whether, so xi to xj you want to increment by delta. So you store this in the pseudocode, we will give the pseudocode, so there we will store everything in an array of size 2n. So the pseudocode of multi-increment. I, j, delta. So what we will assume is that you have access to this array of size 2n. Did we need 2n or 2n minus 1? I think for this example of 8, you needed only 15. So I can also manage in 2n minus 2, I guess. So an array of 2n minus 1 will store the whole tree, the complete binary tree, with values from the array that you were given. So let us say the array was of had n prime many integers. So I am taking n prime because last day we assumed for simplicity that the x array is of size 2 power. What if it is not? In general, your integers, number of integers will not be a power of 2, right? So you will do what? You will just go to the next 2 power. So n prime is the actual length size of the array, and just take a prime, just take a 2 power above n prime, call that n. So leaf values from the actual array. So that will be stored in what part of A? In the later part, right? So the later part n prime many. So basically n minus 1 to 2n minus 2. Okay, that is the part where the leaf is stored, and 0 to n minus 2 is the part where the rest of the top part of the tree, internal nodes, are stored. Okay, so leaf values, so n prime will in general be smaller than, less than equal to n. So the left part of this array, you store the values of x. Remaining part is inaccessible. You don't need to access it, such that n by 2 is less than equal to n prime is less than equal to n, equal to 2 power. Okay, so n prime is the actual number of integers. Take n, which is 2 power just after that. So roughly from n by 2 to n stores your leaves. That is the leaf part, and above n by 2 or before n by 2 is the internal node part. That is the complete binary tree semantics, or the skeletal structure is that. So this will be important because in the pseudocode you need exact formulas to go to the parent and go to children. So now we will do that. So when you say, when multi-increment query says I comma j, what does I mean in the array A? Everything has to be shifted forward by n minus 1, right? So like I equal to 0 would mean the first element in this A n minus 1 array. So 0 maps to n minus 1. So we do that first. So I we change to and similarly j, and we can remember that x n minus 1 is a left child. Okay, so this is how you orient yourself in the complete binary tree. So remember that not xn minus 1, x0. So x0 is your leftmost leaf, and then x1, x2 dot dot xn prime. So x0 has to be placed in the location n minus 1. Okay, this is what the translation is. And so then so now the steps that we saw yesterday. So AI and AJ we will immediately increment. AI is the left one, so this we have incremented. Now if j is greater than I, we'll increment that also. So now AI and AJ both are incremented. Now we have to focus on the middle part, right? So for the middle part we will, like in the example you had 0 to 6, so 4 to 29. So 4 and 29 we, like in the second tree, 4 and 29 we have added this blue 10. And then we have to look at 14, 9, 17, 23 and 21. Right, so now we have to move to that part. So in that part you have to check whether there is some middle part between I to j, right? So which means that the parent should be different. What is parent of I in the array? Around half, right? So I minus 1 by 2. So if this is different from j minus 1 by 2, then you have space between I and j. So you move to that update. So what are those updates? So let's recall, since it was yesterday. So this green part, so if xi or if u is a left child, then you want to increment its sibling. And if j is right child, then you want to increment its sibling, otherwise you will not. So we'll copy that. How do you check whether I is the left child? Should I be even or odd? Yeah, so if I is odd, then it's a left child, so you increment its sibling. Sibling will be I plus 1. Okay, so this is the case of left child, and if j is the right child, how do you know that j is the right child? Should be even. And what is the sibling of j? When it's the right child, then the sibling is minus 1. So this can be done seamlessly in the array, but to make sense of the formulas, you have to actually keep in mind the tree structure. So if I is left child, then the sibling is updated, if incremented. If j is right child, sibling is incremented, otherwise nothing happens. And then you should move to the parent of these two. So, well, technically, to use parenthesis, okay, so this I think finishes some part. This is the while which is done. And yeah, that it also finishes the if condition j greater than I. And I think that's it. So this is the end of the function. Okay, so that's all. So this is the implementation of what you saw in the last class. It gives you all the details. So I to j, I and j you immediately increment, and then you decide whether which one is left, which one is right, and accordingly update the sibling, and then go to the parent. If the parents are different, then you know that there is a gap. So then the while loop will continue. If there is a gap between them, then the while loop will continue. If the parents are the same, then there is no gap, so then the function ends. Okay, so this is the pseudocode, and the execution of this you can see on that example 0 to 6. Any questions? After incrementing AI, we are incrementing AI, we are incrementing AJ. and then after that we are moving to the parent. No, no, no. So the sequence is the following: AI is updated, AJ is updated, then the siblings are updated, then you go to the parent. Yeah. Yes. Then the siblings are updated. Then you will go above. You have to do it level by level. Okay. So, yeah, so if this is clear, so this is a complicated algorithm, but now hopefully it should be clear with the example and the pseudocode details. So what you can learn immediately is that the time complexity, this will be the height of this tree. So A is the array, but if you see it as a tree, then it's the height that determines how many iterations there are. Because every time you are making progress and going above, right? So this is less than equal to log n. So this, for this you need to work out the complete binary tree formula. And that n prime is very close to n. Okay, so I should maybe say in terms of n prime then. So then I should just say maybe size of the array, number of integers you had. Yeah, so that is all in the big O. So the number of integers you had in the array, whether it was 2 power or not, still everything will work out and you will get log of that. Okay, this is a general pseudocode. Any questions? So next is the reporting mechanism. How do you report the value? So value is stored somewhere in the leaf, in the ith location. In fact, technically it will be n minus 1 plus I location. Is it stored in the leaf? Internal nodes also have increments in general, right? So this is getting this complete binary tree. So there is a complete binary tree which is stored in this array. It is augmented with the increments in the internal nodes. And leaves have some integers, but there are also increments above. So how do you compute the correct value, report the correct value of xi? So you have to take the search path and account for the increments. So the accounting has to be done in this. So you have to basically add the values in leaf to root path. So the place where xi is supposed to live, that is in the leaf, so you go there, so you will get some integer, but then that is not the final answer because many updates might have happened before, multi increments. So you have to account for all those increments, and they are arbitrary many. So they are present in the upper structure. So you go from leaf to root, and as you see increment, you increment. So that we will do in the pseudocode. So first you correct I, and you maintain the temporary value, initialize it to 0. If you are not at the root, then you have to do the going above the leaf to root path. So increment the value with the current internal node or leaf value ai. Right? So these are the increments or the original value. And then you move to the parent. So this is the going up part. And you keep doing this till you reach the root when I is equal to 0. So at that point you have the correct value, so you can return it. Is this clear? So this is why we were storing the increments, so that when we report, we can add them up in the search path, which can be seen in the example. So for example, you wanted to report the value of 5. How will it work? Report 5. So report 5 means that you will start with 21, and then then you will go to the parents, that will be plus 10, and then 0, 0, so you will get 31, right? So, and you can obviously do in any order, so you can multi-increment, then report, then multi-increment, then report, and so on. Arbitrary orders, but correct values will be obtained. Okay, so this again is just as many steps as is the height, so that you can show. Okay, this is also log of n prime, the size of the original array. And obviously the data structure is not too big. Okay, so it is in terms of input size, it is linear, and in terms of time, it is in terms of space, let's call this, so this ds takes space. So in terms of space, it is linear, and in terms of time, it is log. Okay, so this is the best possible. Any questions? So this is a very useful data structure. For example, this you can also use in graphic applications, like if you have like Google Maps has maps. So when you zoom inside, you see more and more detail, right? But if you were to call all that detail at once, then your smartphone will crash. So you don't want to call everything at once, because you want to call when you zoom in. So the zooming in is basically walking in this tree. That is the search operation. Okay, so the interval is getting more and more precise. So as you get to a smaller and smaller interval, you move down in this tree. So when you reach a node, then you call the memory for the details of the map, for example. Okay, so this is a very important idea. Without this, Google Maps will not exist, because it will not be able, when you zoom, the image will break. It will take so much time. So it is the log here which makes it extremely fast. So you see as if you are seemingly going inside the map without the graphic breaking. In fact, there is even a movie on this. You can watch on, I think, Netflix. So you can use this idea in 2 dimensions. Right now it is just a single interval, but you can also use 2-dimensional intervals. Then you will be able to do the map problem. So use this to solve windowing queries. Let's say in a map. Okay, so this is the feature which is zooming in Google Maps or Google Earth. So Google Earth has extreme amount of data, because these are videos or images. Right, so everything cannot be called at once in your smartphone. So it is called only when you fix the interval, and then only that small amount is called. As you go to a deeper interval, then a bigger image will be called. So the calling from the internet is happening on demand. So for that you need a tree structure to be maintained at all times. Okay. Next problem is similar. So I think we can finish it today. It's further augmentation. So that is dynamic range minimum. So here, range minimum you have seen before, and you also saw a data structure, which was what size? For array of n, it was n log n, right? So basically for, it was storing somehow powers of 2 size subarrays, minimum of those. So now you will see it in full beauty in the tree form, where you are also allowed to change the array. So you can change any element in the array, and then obviously your data structure has to change, because the minima will change, right? And still everything will be as fast as in that, and space required will be smaller. So now you want to maintain a data structure for list of integers such that the 2 operations are efficient. So these 2 operations are report min from I to j. Okay, so report min is as before. In that ij interval, you want to report the minimum in that range. So it's the same thing as in range min. But the twist here is that it's dynamic, so things can change. So you can update the ith entry. So xi can be suddenly changed to a. Okay, so in a sense the whole array, the array is continuously changing. So if you use your first month algorithm, you have to continuously change that data structure, right? So that is not good. So now we will see after so many months a very advanced method which will do this much faster, and you are allowed to update. So like in this multi-increment, we augment the tree data structure further. So already we have augmented it with this interval tree skeleton. What can you do in addition now? So there you were storing increments. Here you should store minimum, right? So you have the tree, complete binary tree, you have the leaves, have the array x. Now in the internal nodes, there is the indexing is by the intervals, but you can store, instead of the increment, you can store the min of the subtree. Okay, that will be, so it's a different augmentation. So put min of the subtree in the internal nodes. Okay. Yeah, and the interval idea will be continue to be used. It will be helpful here as well. So also what will be helpful is the single array. So store this tree data structure in the array of size 2n minus 2, and x is n prime, and n is a 2 power close to that. So n is the least 2 power, which is just above n prime. Right, so you have the complete binary tree. And also an interval tree. So all these structures are simultaneously present in the array as before. So let's first see the example. So the array is this in the leaves. So 4, 14, 9, 17, 23, 61, 29, 91. I think this is 6. Okay, and so this is x. These are the locations. 0 to 7. What do you fill in the internal nodes? So internal node is kind of this heap property. So you put the min in the internal node. So you put 4 here, 9, 6, 29, then 4 here, 6 here, and 4 here. Okay, so this whole thing is stored in A, array A. So array A has in this case 15 integers when you were given in the input only 8. Okay, so this is the augmented tree data structure. What you want to do here is you want to, let's say, report the minimum from 1 to 5. So how will that work? What is the fast way to calculate the minimum from 1 to 5, which is values 14 to 29? So this is not just a search in a binary search tree. You have to use the interval tree property. Right? So you have to decompose 1, 5 interval as basic intervals. So what is that decomposition? First one is 1, and second 2, 3, and then 4, 5. So into, this is the decomposition into 3 basic intervals. Or basic interval nodes in the tree. Right, so where do they live? Where is 1? So 1 is here. Where is 2, 3? That's the red 9 one. And 4, 5 is red 6 one. Right, so somehow these are important nodes for our business. So for 1, 5, reporting the minimum from 1 to 5 entries, locations, these are the 3 key nodes. What next? Just take the min of these 3. Right, that's what the answer is. So min of 14, 9, and 6, that is 6. Okay, so 6 is the answer. Okay, so we'll use the interval tree property, we'll get the decomposition, and then from the decomposition we'll go to those venues, those locations, those nodes, and calculate the min. So how many such nodes will be there? How many basic nodes are needed? Exactly, that is log n. So we had a lemma, this one, 0 to n minus, so x requires 2n minus 1 intervals or nodes, basic intervals, and for any I comma j interval, you can decompose it into log n many nodal or basic intervals. Okay, so that proof goes via height of the tree in BST search. So if you have done that, then you know that min of only log is needed. So that's very fast. Okay, so this is where the log of n will come from. So how will this work? So I will not give the pseudocode, but how will you find these three intervals? Same as in that case, in the old case. How did you decompose I comma j? So you go to the leaves where xi and xj live, and then you keep moving above till the parents are equal, right? So that is what gave you the decomposition of I comma j. So this pseudocode you have to modify. Is the same picture. So here in 0, 6, you got 6 will be alone. Then after that you will get the second blue tick, which is 4, 5, and above that you will have the third blue tick, which is 0, 3. So you have to identify. You have to remember those. Actually, in the pseudocode, you don't need to remember. You just keep taking min with whatever you see. Okay, so you will, in the end, you will get the min of these three. So that is the pseudocode. So modify the multi-increment pseudocode to find the min of these basic intervals. Okay, so the same pseudocode, you modify it and find the min of these. You don't. So instead of adding the increments, here you are doing min. So plus is replaced by min everywhere in the pseudocode. Okay, so you just have to modify that. And you have to do this in log n time ultimately. So this will be doable in log n time. Okay. How do you update now? So let's say you want to update index 1. You want to make it, let's say, 3. How will that work? So index 1, the leaf there is storing 14. You want to update it, make it smaller, equal to 3. How will you change the data structure? So this is just search. This is like reporting pseudocode, right? You go to that leaf where 14 is stored, change it to 3, and then from here go to the root, right? So the internal nodes that you will visit, you have to change the values if needed, right? So the changes will be that this has to repeat, this you will replace by 3, and maybe we write the original values. Okay, that. So originally they were, it was 4, 9, 6. Okay, these were the original values, and now we are changing them. So 14 we update to 3, and then when we go to the parent, we see that there is a problem. Right now 3 is smaller than 4. So you have to change this. Then when you go to the parent, you see again there is a problem, and again. Right? So just in the height of the tree you will change, you will make the changes, and everything else is correct. Fine? So this pseudocode you can write just like report we saw today, report I, similar to that. To update the tree data structure. Going bottom up. Okay, so change the leaf in the array. You know all the formulas how to move to the parent, and that will correctly update your augmented tree, augmented with min in this case, and that is also very fast. Okay, so we have a similar sized data structure, and time is also extremely fast. So this completely solves dynamic range min. Take space, size of the original array, input array, or well, the number of integers you want to store, because you actually you are not inserting integers. So whatever integers were given in the beginning, that many, and then you can update them. Their values can be changed, but not their size. So it takes space this much, and queries take log of that time. Okay, so this is a much better quality solution than what we had seen before in the first month, right? But it needs a lot of advanced methods in designing and analyzing this data structure. Any questions? Okay, no questions, then I guess we can stop. You can try your hands on designing a data structure which can do both. So both multi-increment and reporting min. So augment both these augmented data structures. So 1 and 2. So first is multi-increment. And second is report the minimum, range min. Okay, so multi-increment, you saw the interval tree idea with increments. Report min, you saw this idea with putting min. Now you want to do both in the same time as an exercise.